Yes. So good evening, everybody. So we'll start with resonance today. I saw some questions. I was just reading the chat session. Dhruv, you want to know more about ozonosis? We'll wait. We'll finish off this chapter and then do. Okay, not a hurry. Okay. So I'll teach you, not to worry. Okay, fine. So we will start with resonance today. So let me just give you a brief idea why all this started. Okay. So why this concept came for resonance? Okay, let me give you a small story. Not story, it's a fact actually. The thing is, they first started with benzene. I hope you all know the structure of benzene by now. So it is like this, right? This is your benzene. Okay. So how is if I write the complete structure, it will be CH2 here. Everywhere it will be CH2. Sorry, CH. Okay, CH. Now, what is, see, it has got an alternate single and double bond. Okay, what is this double bond? This double bond is nothing but the pi bond. Right? All the single bond, the first bond is all the sigma bond. Okay, so now if I take the structure like this, if I draw, okay, the pi bonds are all usually, the p bonds, which are like this. Okay, sigma bonds will be overlapping like this, and the pi bonds will be like this. Okay. So now you have all these p orbitals, right, lined up. So what will happen is these electrons in these pi pi bond or p orbital, they all will just move because they're all close. They have some space, so they'll all move like this. Okay. Now, how did this come? As I wanted to tell you, let's see. You can see the structure. It has a single bond and it has a double bond, right? And we all know that the single bond length is more than double bond. So I think it is there in your, because why I'm telling is in one of the JE paper, they had asked the bond length also here. So the bond length of double bond is 134 picometer and single bond is 154 picometer. Okay, very small. Now, so how did, when you see the structure, you should get two bond lengths. Okay, but when they inserted this compound, not insert means you have you have machines these days where when you put the compound, okay, then it will give you all the data. Okay, the machine used this XRD, okay, X-ray diffraction pattern. So this will give you data about the crystal, the structure, the bond length, bond angle, everything, all those details it will give. So to their surprise, what they found was, instead of getting a single bond length and a double bond length, they got a single bond length, not single bond, a single value, I would say, single value, that is almost the mean, that was 139 picometer. So this made them think, what is happening? It is actually having a double bond and a single bond. Then what is this 139 picometer, which is just giving you an average of these two bonds? Okay. Then they came to know that, these pi orbitals, okay, these electrons in this pi orbital, they'll just rotate, so you have a sandwich structure. If you see, benzene has a sandwich structure like this. Okay. You have top one electron cloud and bottom one electron cloud. Okay, so it's just like this. You have an electron cloud here and an electron cloud here. Okay, this is planar. Your benzene ring is planar. Okay, so because of these pi bonds, the electron, they like shift, they keep moving. So this concept led to the theory of this resonance structure. Okay. So why I gave you this data is because they had asked in one of the competitive exams about, I don't remember which one. So one of these values, so you should know. Okay. So now, so what are the conditions for a resonance is, you can write down. It is, resonance is nothing but shifting or movement or displacement, okay, or displacement of pi electrons. They don't stay in that place. They keep jumping, hopping, okay? Pi electrons, or we can also take into consideration the lone pair of electrons. Okay, so this is the thing. So if you can see the textbook, you have an example here, or I can show you for benzene itself. So let me take this example in double bond O minus. Okay, this is plus charge. So now what is the other thing you can take? See this minus charge. This can move here and this can move here. Okay, so the other resonance structure will be CH3 and O minus, and this will become double bond. So these are the two canonical forms of resonance. So what is happening? The pi electrons can move, are moving. Okay. Now in benzene also you can see that the electrons can shift like this, then like this. Okay. So now more about benzene. See, I will write the structure for benzene also. Here you have two resonance structure, and here you can see the pi electrons can move like this, then it can get shifted, and this one can get shifted. So the other resonance structure, I would write it like this. That is like this, like this, like this. Okay. So it keeps on rotating. Okay. So that is why we write a hybrid structure. So if they ask you resonance structure, these are the two resonance structure, and the hybrid structure, that is to show both together, we will write it like this with dotted lines. The electrons are like rotating. So now I think you will know why we are writing this one. Why we always put a ring inside the benzene ring. You think we are all so lazy to put dots and show, right? So we will just put a ring. Okay, that is a concept actually. That's why we use this ring. So now these are the resonance structures. Okay, then you have another concept here. More the resonance structure. See, each one will have some resonance energy. Okay, there will be some difference between this energy and the hybrid structure. Okay, so the difference between this energy, so this is called the energy of these canonical forms are called the resonance stabilization energy, or we can also call it as simply resonance energy. Okay, and this hybrid structure obviously will have one energy. This also will have the energy. This, so the difference between the energy difference between these two, okay, will give will tell you how stable is it. So the more the stabilization energy. Okay, so when you have more canonical forms, these are called the canonical forms. Okay, more canonical forms, more resonance energy. Okay, that is the difference in energy between this structure and this structure, more stable it is. So we study resonance just to see the stability of the compound. Okay, I hope it's clear now. So now, as I told you, we will see what are the points. One is movement. Okay, movement of pi electrons, as I'll write it again, or shifting of pi electrons or lone pair. The second one is point. Okay, it is within the same molecule. It's not like transferring from one molecule. So this effect is basically intramolecular property. Okay, and they have clearly given in your textbook. It's just a hypothetical thing. See, we know all this. So just to give an explanation, so it is just a hypothetical concept, okay, or an imaginary concept. Okay, so I would say this is a hypothetical concept. Okay, and as I told you, the hybrid. What is that hybrid called? Resonance hybrid. It's nothing but it is a combination of all resonating structures. As I told you, if I show benzene, this is your hybrid structure. Okay, fine. Now we can do some textbook questions itself. So we can see here. Then another example is carbonate. Okay, CO3. This is your textbook question itself. CO3 2-. They will ask you, give the resonance structure of carbonate ion. So what you have to write? you have to show like this, CO minus O minus double bond O. Okay. So what can happen? Now this electron can move here. This pi bond electron can move here. So the other resonating structures would be O minus. This will become double bond O. This will become O minus. Another one. Okay. So we can move this one here. Okay. And this one back here. So the other structure would be O minus. This can be O minus and this can be double bond O. So you can see there are three canonical forms, three resonance structure. Okay. How will I write the hybrid structure now? Hybrid structure, I will have to see the electrons are moving between all those three bonds, right? Like, here this part, and this part. So I will write it, or I will draw it this way. Let us see. Let's put one oxygen everywhere. Okay. So the electrons are moving like this between all three. Okay. So now the charge is also moving. So let me put it as delta minus, delta minus, delta minus. Okay. So this is called your hybrid structure. The real structure, I would say. Okay. So now, what are the basics? Now, why these resonance structures? Okay, what are the points behind this? Okay, for what kind of compound this resonance will be exhibited? Okay, so the first one, so we also call resonance as conjugation. Okay, what are the conditions for a compound to exhibit resonance? The first point is it has to have an alternate pi bond and a sigma bond, followed by a positive charge or a vacant. A positive charge means it's a vacant orbital. The electrons have moved, so it is having a positive charge. Okay, that is what is pi bond, a double bond, a single bond, and we can also show it as double bond, single bond, double bond, single bond, and a positive charge. Okay, the second point, a pi bond and a sigma bond, followed by a lone pair of electron. Okay, we will show it either like this, a lone pair, or we can also show it as minus. Okay, the other one, it can also compounds which can have even a free radical. What's a free radical? A single electron. So those compounds, that is free radical, they can also show resonance. Okay, or in general, if I talk about benzene, what can I tell? It has a alternates pi bond, sigma bond, pi bond, sigma bond, and so on. Okay, so these are the conditions for a compound to exhibit, that is conjugation. Okay, sigma pi. So like this. So these are very important. You should know what kind of compounds can show resonance. Okay, it should have an alternate pi bond and a sigma bond, followed by a positive charge, a lone pair of electron, a free radical, or it can be just like sigma pi. Okay, so now let us see let's see some examples for the first case. Okay, the first case, we will have only we'll have a positive charge. So let me just show you the first case, that is sigma pi and a positive charge. Okay, or a vacant d orbital. So the example is CH2 double bond CH2, a carbocation. This is an example for this first type. Okay, now what is the resonance it can undergo? Now the charge has to move. Okay, so this double bond can move here. Okay, so if it moves here, I will just write first CH. This will become double bond. Now, where will this positive charge, where is it like more now? So here the positive charge will move from wherever the double bond moved to that carbon, the positive charge will be there. So these are, see, you can see double bond, single bond followed by a positive charge. Okay, so like this you can write for many examples. You can take the second example. So this is example 1. Then you can also take an example of a ring compound. That is, let me show you on the next page. Example 2. you can take it like this. Okay, a positive charge. See here, there's a double bond, a single bond, double bond, and a positive charge. Okay, so what are the resonance structure for these now? Okay, so let's try moving this. Now let me move this double bond here. So you will have the positive. So when it moves here, so the positive charge will move on to this carbon. Okay. Now what is the other thing I can write now? I can bring the positive charge down, to the other position. So let me put this double bond here. Okay. So then I will have the resonating structure like this, the positive charge will move here. Okay, that's all possible things are over. So now how will I write the resonance hybrid? Will be as I told you, it is just depicting the three canonical forms. See, it has moved, the electrons has moved, see here, between this carbon to this part. It has not gone to this part, it has not gone to that part. Okay, so we will write the resonance form as like this, as dotted. That's all. You have to be very careful when you are showing. Okay, so now where are the positive charges? Now where are three positions, that is delta plus here. Okay, it has moved to this place and it has moved to this place. So this is your hybrid form. Okay, I hope it's clear. So these many examples. So if I ask you between example 1 and example 2, which is more stable, which one would you say? As I told you, more the resonance structure, more stable the compound is. So in these two examples, we can say that example 2 is more stable than 1 because it has 3 resonance structures and the first one has only 2 resonance structure. Okay, so now like that we can keep on writing. There are many examples, so you can try that out. So the next one is the second one. If you want, I can do another example also. Let me just show you example. Yeah, let me take a simple example. 3. Example 3. Cyclopentadiene with a positive charge. See, every time I'm putting a charge, like, the condition 1. So I can write. Now, where all I can move here? See, you don't have much structure here. Okay, when it moves here, you will get it like this. So the positive charge will move here. Okay, only 2 structures because there's only 1 double bond. Then you can write. So where are the electrons movement? Now it is only between this carbon and this carbon. Okay, so now where will I write the positive charge? It is in this carbon and in this carbon. Okay, so this is the first form. Okay, now let us move on. So you can take some examples and just try it out. Okay, I don't know whether many examples are there in your textbook, but if you can get some, you can try. Okay, now we'll go to the second part. What is the second one? Pi bond. Okay, a sigma bond. Then you have a lone pair or a negative charge. Okay, so let's see some examples here. Example 1. Okay, the same first one, but I will put a negative charge. Double bond CH. It's a carbanion. Minus charge. Okay, now how will I write the resonance structure here? Now this electron can move here. Okay, and this double bond electron can move to this carbon. So the resonance structure would be CH2 minus CH double bond CH2. So only there are 2 canonical forms and the hybrid structure would be CH2 single bond CH CH2. Okay, so where are the electron movement? Minus charge, 1 in this carbon. Okay, the other one in this carbon. Okay, so where are the electrons moving now? Between these 2 carbon and plus 2 carbon. So this is your hybrid form. Okay, so we have another example. I'll show you. That is your nitrate ion. Example 2. So what's a nitrate ion? See, by now you should be knowing what's a nitrate ion, what's a nitrate. Sometimes they won't give you the formula. They'll just tell you write it for nitrate. What is for nitrite? All that you should know. Okay, nitrate is NO3. Okay, 2 minus. Okay, so now you have N double bond O minus O, same like carbonate. Okay, now you have another one. So where all it can move? This can move here. Okay, and this can move here. The other structure would be O minus double bond O minus. Okay, then you can also write. Now what can happen? Yeah, this one can move here and this one can move here. O minus double bond O minus. Okay, so 1, 2, 3 structures. That's all. There's no other. It has taken all the forms. Now the resonance hybrid for this would be N O O. So you can see between all these 3 bonds, like the electrons are moving. So I would show it like this. And where are the minus charge? Between all 3 O. So I will put it as delta minus. Sometimes, okay, they can also show, because each book will tell you something. Sometimes they will show you within the bracket, they will write this N, O. So don't get confused. Instead of showing the individual minus charges, they can show like this. And what is the charge here? 2 minus. So you can also write it like this. So there's no harm. Either way, you can show it. Okay. Now, so let me, as I told you in the first one, I was telling you the stability of the compound. Okay. Now here, the more the structures, more stable. Here you have something, a rule. Okay. Suppose I'll take an example and show you. Suppose I'm taking this example, CH2 double bond CH NH2 dot. See, this molecule does, see, all these structures what I showed you had the charges in it, minus charge or plus charge. Okay, here you can see, for this also I can show that the double bond electrons can move here, and sorry, the lone pair can move to this one and double bond electrons. So you will have a structure CH2 minus CH double bond NH2. Because a nitrogen has donated the electron, nitrogen will carry a positive charge. Okay, so the resonance structure would be, sorry, the resonance hybrid would be CH2 CH NH2, electron movement between these 2 atoms. Okay, and you can show, see, this carbon has a minus charge, so this will be delta minus, and this one has delta plus charge. Okay, so now how many resonating structures? These 2 are the 2 resonating structures. Okay, now in this, if I ask you, among these 2 structures, which is more stable? Okay, so you can see this is neutral because there is no charge, and here it is charged. This molecule is charged. Okay, so now whenever I give you like this, okay, so in that the neutral molecule is always more stable than the charge. So that also you have to remember. So here you can also write neutral compounds or neutral form are more stable than charged ones. Okay, this is another clue. Fine. Okay. So here there's one more thing. Okay, I'll just tell you that CH3, C double bond O, H. Okay, so now here what can happen? Now this hydrogen, okay, can move to this oxygen. So you can write it CH2, okay. Imagine this can move here and a hydrogen from here. Let me write it like this. H, okay. One of the hydrogen can move here, okay. So it will become CH2 double bond OH. Please, because many people get confused, that's why I'm stressing on this, okay. Whenever it is like this is not like, resonance. This is, what is this? This is tautomerism. I hope you remember. This is called tautomerism. This is not resonance. Okay, fine. Now you have a lot of examples like that. Let me give you one more with a benzene ring. Okay, with NH2. Let me take it like this. Example. This and NH2. This is called aniline. Okay. So now what can happen now? This double bond electron can move here. Okay. And this, see, once it moves here, you should also check for the valency, right? So this double bond electron will move to this carbon. Okay. So you will write the structure. So this will have a minus charge now. So these two bonds here, this will become double bond NH2 plus. Okay, this is there in your textbook also. So now, what is the other structure? What I can write? This electron, now it moves here. This double bond electron will move to this carbon. So you will have a minus charge here. And you will have double bond NH2 plus. One more structure. So this electron can move here and this can move here. Okay. So then we can write it like this. Minus charge, double bond NH2. Now I can also end it up like this. Now this electron can go back to this position. Okay. And this double bond electron can go to this nitrogen. So the other structure would be NH2 minus or lone pair, anything. Okay. See here, I started with a double bond here like this. Now see here, I ended up like this. Just the opposite. Okay. So now, so how many resonance structures? So this compound is very stable, and how many resonance structure? 1, 2, 3, 4, 5 resonance structure. So we can say that this is very highly stable. Okay. One more thing what I want to tell you is, okay. So one sec. Okay. Whenever you have the electron, so we know that in a benzene ring like this, okay, if there is some group here X, okay, now which is, what is it? It's donating electron to the ring, okay, so that is what is happening. You are getting a minus charge in the, so we know that this will be the ortho position, this is your meta position, and this is the para position, right? So now you can see where are the negative charges now? They are in the negative charges are on the ortho and para positions. Okay, and remember it is a negative charge which is moving around the ring. Okay, and they are in the ortho and para positions. Okay, such effect where electrons are inside the benzene ring, that is a negative charge, okay, in the ortho para position. So this is called your plus R effect. That is, if I have an NH2 group, okay, in the benzene ring, so that group is an ortho-para directing group. So I can call this NH2 group on the benzene ring as ortho-para directing group. Okay, so I'll just tell you what it is. Next chapter, you'll be studying a lot about this. Okay, imagine I have an aniline compound, and we all know that it can undergo only, benzene ring compounds can undergo only electrophilic substitution reaction. Why? That is what is electrophilic. Okay, so which will have a plus charge, positive charge only can come and attack them. Why it can attack? Because the benzene ring, as I showed you, it has a sandwich structure where you have electrons above and below the plane. Again, another electron, like a minus charge, a group having a minus charge comes near the benzene ring, it will start repelling. Okay, it will not react. So that is why we'll have only groups with positive charge coming and attacking the ring. Okay, that's why it's called electrophilic substitution reaction. Okay, electron loving. Now, if I give, imagine I am having a Cl, okay, plus charge. Okay, we have Cl plus and minus. Imagine this Cl plus has to come and attack the ring. Where will it go now? You can see where are the negative charges. So we know in the aniline structure, we found that the negative charges are in the ortho position and the para position. So when I react with Cl plus, it will give you two products. Okay, NH2Cl here, plus this is your ortho product. Okay, and the other one is your para product. Okay, this is your para product. Okay, now among this, if you want which is major, I would say this is major. Always para is the major product. Obviously, the ortho product is also formed. Why? Because why ortho is less? Because you have a group here, okay, and you want to come and sit near. See, there's a small chair. Okay, already this fellow is sitting here. Okay, now this chlorine has to come and adjust itself. Like it's finding it very difficult. So it will go to a convenient position, take another chair, or come and sit here. Okay, so that's why para product is always a major product compared to ortho product. Okay, so now we can say that aniline, okay, will show positive resonance or plus R effect. Okay, and it will give you ortho para products. Okay, so when you learn next chapter about hydrocarbon, you'll see ortho para how it is formed. Okay, so now coming to the next one. Next kind, let me move on to the next type, that is, I didn't tell you about the this thing. Let me just finish off that also. So I've given you the plus, I don't know. Okay, anyway, let me just not go back. I'll just give you an example from your textbook itself. That is NO2 group. Let me take an NO2 group. This is not part of this example. It is a part of the previous example. That is, let me take it as, please don't get confused. This is a different compound for the previous set. Okay, this is, so what is this called? This is called nitrobenzene. Let me write the resonance structure for this. Now, see, in the previous one, it was electron donate, like it was electron donating. The electrons were coming inside the ring. See, I'll just show you so that you don't get confused, so that you can have time for you don't have to mug up things. So NHH. Okay, see, these electrons cannot be pulled by hydrogen, right? Because it is not electronegative, it's not more electronegative. So this electron can be only pulled by the ring. So that is why the electrons are entering the ring. Okay, now here if I take, okay, so here you have the charge. This is your minus charge. Okay, now here NO2 group is a electron withdrawing group, because here the electrons see, if I compare the benzene ring and this oxygen, okay, or let me consider this oxygen, okay. So this double bond electron cannot come inside the ring, okay, because your oxygen is more electronegative. Oxygen is more electronegative. So this double bond electron will go towards oxygen and not come inside the ring. You should be very careful, okay. So here, this one I can't do it like this because hydrogen is not electronegative, okay. But here oxygen is being more electronegative. This double bond electron will be pulled towards oxygen. So when it is pulled towards oxygen, all the double bond electrons will start moving towards that side, okay. So let me write the resonance structure for nitrobenzene. It will be N. So actually it is coordinate bond because it has, okay, so this is the structure. So as I told you, electrons will be pulled. So what will happen? This double bond electron will go to this oxygen. As a result, this double bond will move here because your valency also will be satisfied. So the next resonance structure would be NO. So this will become O minus. So this double bond has moved here. So obviously this will be. So once it has moved, so what will have? This one will have, this will have a positive. It's not coming inside the ring. It is going away from them. Okay, so this is the, so this is having a positive charge. Okay. So now what is the next resonance structure? Okay. So this one can move here. Okay. So this positive. Okay, and the positive charge can move to this place, so you will have the structure. Okay, the other resonance structure. Now this can move here, so you will have a positive charge. Okay, obviously in all these cases, nitrogen will be positive. Okay, so now what is the next one? This one can again come back here. So you will have the next structure. And this one will move here. Okay, so this will be double bond O. Okay, see, we started like this. Okay, and we have ended this way. So again, here also 5 resonating structures. Okay, and how will I write the hybrid form? It will be between all that. Okay, the hybrid form would be, okay, and double bond O minus. Okay, sorry. Fine. So there are 5 canonical forms for the structure. Now, what you have to remember here is, look here, I told you the benzene ring can undergo only electrophilics. Now, what will happen? A positive charge is coming. So now you can see in the ortho and para positions, that is this position and this position, already a plus charge is there. Now, where is that little electron density present? It is there in the meta position. Because ortho and para both have the positive charge. So that if I do a substitution reaction, an electrophilic substitution reaction, so you will, let me just take this example, the same thing, NO2. If a chlorine is coming into picture, okay, substitution. So now, as I told you, in the, this is also plus charge. Now you can see in the ortho and para, the positive charge is there. So where will it go and attack? So this one will give you a meta substituted product, that is NO2. Okay, and you will get CH. Okay, so now this is NO2. Okay, that is this nitrobenzene is so it is coming like, you know, it is dictating the incoming positive charge to go and sit in the meta position. So nitrobenzene is a meta directing group. And when you have the positive charge in the ortho position, movement of positive charge, so these kind of compounds will show minus R effect. So please, you should not get confused between plus R and minus R effect, because they'll give you a lot of compounds like this. Okay, so you should not make a mistake by writing para instead of meta or and so on. Okay, so you have to be very careful where you have to put this substituent, whether in the ortho-para position or the meta position. Okay, so they have given some order in your textbook, plus R and minus R effect. So now you don't have to mug up. You don't have to mug up. Okay. You can just see where will the electron move. Will it be pulled away from the benzene ring or will it enter the benzene ring? Okay. Just seeing that you can tell whether it can form orthopara or plus R effect or minus R effects. Okay. So let's try. I'll just give you some 2-3 minutes. You can try this, which is not there. I'll give you 2 examples. One is an aldehyde. Okay. Other one, I'll give you a simple one, which is alcohol. I've also shown you with electrons. Okay. Now, please tell me, you can just draw and tell me aldehyde, benzaldehyde, this is called benzaldehyde. And this is your alcohol, this is also called phenol. Tell me, one is what directing group and 2 is what directing group. Okay, let me just see how many of you answer. Yes, Dhruv is right. Yes, Mukhil is right. Ashwin is right. Yes, minus R. Atharva is right. Karthik is right. Yes, Kamal, Shiju, Srinidhi. Very good. All of you. Very good. Aditya, Akhila. Good. Very good. Nandita, all are right. Okay, let me just show you. Okay, so as I told you, they have given a big group, like, plus R affects some 5-6 compounds, minus R affects some 5-6 compounds. So please, you don't have to remember at all. Okay, you can just by seeing, you can say whether. So I'll tell you. First, let us try to do this one. Because if you don't know this, again, you will find it very difficult for substitution. Okay, the first one is benzaldehyde. Now we know oxygen is more, when I compare this carbon, oxygen is more electronegative than the benzene ring. So now how will the movement be? They can ask you even in school, okay, to write the resonating structures. So this double bond electron will move to oxygen. So automatically, to satisfy the carbon valency, this electron will move here, double bond electron. So the next resonating structure would be double bond CHO minus, right? Okay, so now the electron has moved out, so this will be positive charge. Okay, so next one will be, so if this one moves here, the positive charge will come here. So you will have double bond CO minus H. Okay, the next one, if this electron moves here, you will have. So please practice all this, because they might ask you in school. The positive charge will be here, HO minus. Okay, so next last structure would be, okay, one sec. Okay, let me write the next structure. So this electron will move here and automatically this one will move back. So you can say that it is CH, it has come to its normal position, and you will have, okay, see the resonance structure, it started here and now it has moved this way. Okay, so these are the 5 resonating structures. Okay, so now you can see from the structure that in the ortho and para, what is there? Positive charges moving. Okay, so that is, it is minus R effect. Some of you had just told minus R, that's also good. Okay, so where will the incoming substituent get attached? So it will go, so it is also your benzaldehyde. Okay, your benzaldehyde is a meta-directing group. Fine. Okay. Now the next one, what did I give you next one? Phenol. So let's do for phenol now. H. So now you know hydrogen is not electronegative. It can't pull the electron. Now what has to happen? This electron now can move only inside the ring. Okay, once this moves here, this one will move here. So the structure would be minus double bond OH. Okay, so now the next one. So this one will move here. So the negative charge will move here. Then this one can move here and this one can move here. Okay, and the last structure, this one can move here and this one can move here. Okay, it has gone back to the electrons. So you can see this structure and sticks. So again, 5 resonating structure. So you can also say that, so where will the incoming electrophile come and attack? It will be attacking because minus negative charge, the charge density is more in ortho and para position. Okay, so it will go and attack the ortho and para position. So phenol is a ortho para directing group. So if they give you any reactions, you have to just put the substituent depending on the group, directing group, and it will also show plus R effect. Okay, I hope it is clear for you. Okay, now let's go to the next kind example where we will be studying about the free radical. Okay, I think this is the third one. Okay, third type where we have pi sigma free radical. Okay, so now I'll show you with an example now. So CH2 double bond CH CH2 dot. See, there is a pi, sigma and a free radical. Okay, now if this double bond comes here, okay, this free radical will move to this carbon. So the structure would be, see, there is always a movement. Okay, so that's what is called resonance. So this one will have a positive thing. Okay, so now you can also write one more structure. No, I think only these two are possible. Okay, so these two are the resonance hybrids. Now when I come to, I'll show you another example. With a ring compound CH2 dot. Okay, so how will I show the resonance structure for this? Okay, so see, I told you free radical means it is homolytic cleavage. That is, a bond, okay, is broken exactly into two, taking one electron each. Okay, so now when this electron has to, this free radical has to move, let us break this bond here. Okay, so you will get one, so I'll show you. There's one free radical here and one free radical here. Now this free radical and this free radical will join. Okay, so you will get the next resonance structure would be double bond CH2 and a free radical here. Okay, now I can also write one more. Now if this free radical has to move, now let me cleave this thing. Okay, you will have two dots, one here and one here. So let me write this one here. So these two will form a bond. Okay, so you will get the free radical here, double bond CH2. Now let it again, it can move. So let us break this one. So you will get a free radical here and a free radical here. So these two free radical will join. So you will get a double bond here, a free radical here, double bond CH2. Okay, so these. Then you can also write, that's all right. Yeah. So now it can go back to the same structure. So imagine if I have to break this. So these two will join. So you'll get the next structure like this. CH2 dot. So this will be, see how I started here, how I ended here. Okay. So these are the sticks. So how many structures? 5 structures. So how will I write the canonical form? See, till now I didn't show you. Again, I'll show you now. So these are the 5 canonical forms, and the hybrid structure would be, see, the electrons are moving right from the CH2 group above the ring and the whole ring. Okay. So I will write the hybrid structure. Suppose they ask you to show like this. So the hybrid structure would be, see here, the electron movement here and the electron movement is here. So this is your hybrid structure. Okay, so this is with respect to a free radical. Okay, and we already know that, we have already seen the next type, that is sigma pi pi, that is okay. So the fourth type is sigma pi without any charge. Okay, benzene is a very good example. Then you can also show with aliphatic compounds, long chain, double bond. Basically an aldehyde. So what can happen now? This can move here, this can move here. But now what will happen? The charges will come into picture. So you will have CH2, CH, double bond, CH. This will become O minus. So because this has become minus and this has moved, so this will be having a positive charge. Okay. These are the resonance structure. You see, we have compounds with neutral and the ions. Okay. Now, how will I write the next structure? That's all. Only 2 structures are so possible. No, other one can be written like the CH2 plus. Yeah. The other one, yeah. CH2. Okay, fine. So these are the 2 structures. Let me just see. Oh, there are another carbon also. You can have the positive charge on the other carbon also. So it can be CH2 plus. Okay. So it can be CH, positive charge. Let me just check 1 minute. Yeah, sorry, first one I would say, just I made a mistake here. Okay, see, once this comes here, first let us take only this bond, okay, double bond. So once this moves here, what will be the structure? CH2 double bond CH. So this will be O minus and this would be plus. Okay, this step, first step. Then it will be, then it can move here. Okay, so there are 3 structures, CH2. So this will have a positive charge. So this will have double bond CH, O minus. Okay, so these are the 2 structures. Totally 3 structures. So now which is the canonical form? Sorry. This is your hybrid form would be, the electrons are moving between all the carbon. Okay, so it is here, here and here. Now which is the one which is having the negative charge? Only this one. So all the other where are the positive charges? The positive charges are in this carbon and this carbon. So please don't make a mistake. People put positive on all the 3 carbons. No, wherever the positive charge is moved, only there you have to put delta plus. So the delta plus will be here and delta plus will be here. Okay, so these are the examples. I think I've done only one example. Let me do another example for you. Okay, so let me do it with a benzene ring. Yeah, this I can show you even the benzaldehyde. Okay, so benzaldehyde is also a, so if I take benzaldehyde, COH. Okay, this will show same thing as I've already drawn the resonating structures. So you will have the positive charges moving inside the ring, and so this will also show you minus R effect. Okay. Now we will see. One second. Yeah. So I just want to tell. Let us see another example of the type lone pair, okay, and sigma positive or vacant. This kind of a compound, okay. So an example, see, this doesn't have a double bond. It has a lone pair and a sigma, okay. So example is CH. This is of the fifth type, N, which I didn't mention, but this is also there, NH. See here, you have a lone pair followed by a positive charge. So this compound will also show resonance structure. How this can move, the lone pair can move here. So the other structure would be CH3 NH. Because nitrogen has donated, it will become a positive charge and double bond CH2. Okay. So now this is how we can write. Now please remember the negative, the charge, okay. If it is more electronegative atom, only that can hold the charge. So now both of them have the same charge here. See here, positive charge and positive charge, okay. So it is not, this is not called resonating, but we put it under the resonance concept. So the hybrid would be CH3 and delta plus CH2 delta plus. Okay, and always remember the more electronegative atom here, which is the more electronegative atom, nitrogen, it will not like to have a positive charge. It will always love to have a negative charge on it. Okay, so it will always not prefer a positive charge. So now I have another example which will come under this topic, that is CH3O CH2 plus. Okay, this kind of a compound or ether kind of a compound. So this also will show. So this electron will move here. It will become CH3O plus double bond CH2. Okay, so this kind of resonating structures are also possible, but not found with the fifth category is not found much. So only the first four are more important for resonating structures or resonance to occur. Okay, I hope you all have understood what is resonance. So you should know the ortho-para directing group, that is the plus R effect and the minus R effect. Okay. Now, let us see. So we have seen all this thing. We will see the stability, which is more important, the stability of resonance structures. Okay. The next would be, which is more important. You study all this to study the stability of the structures. Okay. Yeah. So as I told you, we will do some problems now. First one, CH3O. Okay. If I ask you, which is more stable among these two? That is, this one will have, the other resonance structure would be positive bond CH2. So this is of that last type, okay, what I showed you. If I ask you which is more stable, can you see, can it see some answers? Among this 1 and 2, if I say which is more stable? Dhruv has written. Okay, let me just come back and let others also answer. Vishisht is right. No. Wait, okay, I think I haven't told you the rule, so let me just go back. Srinidhi is right. Okay, if they ask you like this, see rule number 1. Here I'll tell you all the rules, okay, to tell about the stability. Rule number 1 is, one sec. So please note down all the rules. More the number of covalent bond, more is the stability. More stable, or more is the stability. So what are the covalent bonds? How many covalent bonds are here? See in this only, see the other two sides, it's all the same. Now let us consider only these two for our calculation. Now there are 2 here and there are 3 here. Now you can tell 2 is more stable than 1. So this is your rule number 1. More the number of covalent bonds, okay, more stable it is. Fine? Okay. So now, let me see whether you can try. Every time I'll give you an example, you people can try. Okay. It is in resonance with, I can write it like this. Yeah. So this rule I have told you, so you people have to try. Which is more stable, 1 or 2? Vishisht is right. Yes, good. Nidhi is right. Adharva is right. Dhruv is right. Yeah. I think all of you got the answer. Yeah, Srinidhi, Terina, Aditya. Wow. Everybody is right. Okay, I've already told you about this. Okay, neutral species. See now the number of covalent bond. If I take here, the number of covalent bond is the same. Now, let me take 1 and 2. We can see the charged species, as I told you, is less stable than the neutral species. Okay, so in this case, 1 is greater than 2. So you can write down rule 2. Okay, neutral species or compounds are more stable than charged species. Okay, so now let us see the next one. I have already told you this, I didn't write, but let me see whether you people can try. After I do the thing, you can tell, I'll tell you the rule. Okay, so the resonance structure of this would be yeah. Can you try this 1 and 2? Which is more stable? Can you tell me? Many of you are getting confused. Yeah, I've already told you this. I just mentioned when I was teaching. 1 is correct. Very good. Arvind, Vidushri. Yes. Dhruv is right. Good. Yeah. If you can give reasons also, I'll be very happy. Good. So what is the rule 3 here? See now, as per rule 1, okay, number of bonds are same. Same covalent bonds. Same number of covalent bonds. Rule 2. Same charges, okay? There is no neutral, both are having charges. So charges are same. So please give the priority order, okay? First check for the rule number 1, then rule number 2. Then after that only you have to go to the rule number 3. Okay, the negative charge on the more electronegative atom is more stable. Now you see here, oxygen has a minus, is holding a minus charge, but here in this carbon is holding the minus charge. Okay, so which is more stable, the negative charge on the more electronegative atom? So the rule number 3 is negative charge on the more electronegative atom will be more stable. Okay, I hope you got the rules for resonance. Now coming to the next one. Same thing, you can also think of, like, I'm not telling you that, but you can, rule number 4. If it is with a positive charge, okay, imagine if it is having a positive charge. We saw an example with a negative charge. Now, if the positive charge should be the vice versa. So, positive charge on the electronegative atom will give instability. So, this also you should note down. Okay. Now, coming to the next one. I hope it's clear for you. So let us see some order of stability, some examples. You can try that. Yeah. So let us do some exercise now. Then we will go to the rule number 5. Question 1. This I have already done, the carbonate ion. Okay, the resonance structures would be let me first write it like this. Let me not move. So if it goes like this will have a positive charge. Let me write like this. Let me just give you the examples. So 1, 2, and the third one, I'm just showing you like this. So can you write the order of stability from lowest to highest? Let me see whether you can try this out. Yes, Adarva, you have to follow the priority order. You just can't jump into the fourth or third rule before checking the first and second rule. Dhruv is right. Bhavanidhi is right. Yeah. I think most of you got it right. Very good. Fine. Very good. Okay. So first, see, that's why I told you first we have to go. I think, I don't know who asked. So we have to go as per the rule 1. As per rule 1, number of bonds. My number of bonds is more in which one? Compound 1. So first write 1. Okay. Now, coming to the next one, 2 and 3. Check for that. Okay. So the most electronegative atom, oxygen, is holding the minus charge. Okay. And the third one, oxygen, is having a positive charge. So 2 is greater than 3. So like this, you have to check rule by rule. This is very, very important. Okay. So now let me give you one more compound. Let me give you a JEE question. Arrange the order of stability. Let me write the fourth one here. Yeah. Can you give me the order? This is a JEE question. Vishist is right. Very good. Karthik is right. Mukhil is right. Akila is correct. Very good. Bhavanidhi is right. Very good. I think you got it. Yes, most of you got it right. Very good. Okay, so rule number 1, number of covalent bonds. Okay, so we can see which one. Okay, as per rule number 1, more number of covalent bond is in 1 and 3. Okay, so we will categorize that. We will keep it as same. Okay, now we can also see that the electronegative, nitrogen is more electronegative than carbon. So nitrogen is holding a negative charge here, but whereas carbon is holding that. So which one will be more stable? So first we have separated 1 and 3. In that 1 and 3, go to the next rule. So it will be 1 greater than 3. So we have finished 1 and 3. Now let us see one. Between 2 and 4. Okay, so number of covalent bonds are same. Okay, again the negative charge is there in nitrogen in 2 and here. So it will be 2 and 4. Very good. Most of you got it. Right. This is your answer. Okay, see, it's so simple. How simple it is to attempt even a competitive question. Okay, so now let us see one more. I want to tell you some exceptions also here. So anyway, before going into that, let's do one more competitive question. CH2 double bond CH and H. 1, 2, 3, and the fourth one. So only 3. Okay, so if you see, the number of bonds are more in 1 and 3. Okay, 1, I told you, now you have to see the neutral species. So this is neutral, so 1 will take the priority. Okay, then obviously next would be 3, then the last one will be 2. So within just 1 minute, or not even 1 minute, 1 second, you can just get the answer. Okay, so now coming to the the deviations from this rules. Okay, so let's see this question. I'll just teach you NH3 plus. Okay, let me take 1, then let me take another compound CH double bond NH3. Okay, so comparing these two, let me know. So 1 and this is 2. If I tell you to find which is more stable, okay, you would say that the positive charge is on the carbon atom in 2, okay, whereas the positive charge is on the nitrogen in the first one. So obviously from this itself we can tell that 2 will be more stable than 1. But this is not so. This is completely wrong. Okay, why? Because if you see the second structure, okay, look here, nitrogen, how many valency does it have? Nitrogen, see here, double bond, then 3. Pentavalent. It cannot be, nitrogen cannot be. Phosphorus can be pentavalent, but nitrogen cannot be pentavalent. It can be only trivalent because it doesn't have any empty d orbitals. Okay, so it is in the first row, first in the group. So nitrogen. So write down the exceptions. Okay. The second thing, structure is not correct because nitrogen is pentavalent. If it is phosphorus, it can be, okay, but nitrogen cannot be pentavalent. So this is not possible, okay. So because the second structure itself is not possible, so first one is stable. So please note down this exception, okay. Now, coming to the next one. The next question. Which one is least stable? So this is again a competitive question. So let me give you the options for the nitrobenzene. One, this is two. These are not resonating structures. These are just three compounds. You have to tell me which is the least stable one. Four. Can you tell me among this which one is the least stable? Yes, Karthik. 2 doesn't exist in the previous question. Yes, Dhruv. It has no d orbital, so it cannot form, nitrogen cannot form 5 bonds. Check, Ashwin. Ashwin, check. Tanuf is right. Shiju. Tanuf Shiju is right. Srinidhi is right. Mukil is right. Akhila is right. Mubin is right. Vishist is right. Good. Just the previous rule. Where have I put chlorine? In the third one, it is a positive charge. Yes, Lakshmi is right. Ashwin is right. Very good. Most of you got it right. Okay, see, nitrogen, just the rule. Okay, I've just applied this rule. You see here, 3 bonds here, nitrogen. 3 bonds here. 3 bonds here. Look here, it is already 4. I told you it can be only trivalent. It cannot be more than that. Okay, so third one is the least stable. Because see here, 1, 2, 3, 4, 5. It has become pentavalent. So it is not possible. Okay. So let's move on to the next one. We have to finish aromatic thing. Let's go to the last rule. Not last rule. There are 2 more rules. Rule number 6. Okay. Now, let me take an example. I'll just give you an example. First, let me tell you with something. X, some species, okay? X, positive charge, negative charge, okay? This is compound 1, okay? Let me take compound 2. X, the same thing. Now, if they ask you, sorry, this is plus. If they ask you among 1 and 2, which one is more stable? Okay, so you have to write that 2 is more stable, is stable. Why? Now I'm coming to the rule number 6. When the two like charges are close by, what will happen? They will repel. Okay, see here, the two positive charges are close to the two atoms here. Here they are separated with a negative charge. So what will happen when the two charges are just between the two atoms which are adjacent? Okay, it will start repelling and that will become more unstable. So you can write the rule number 6, two like charges must be separated far apart. Otherwise, there will be repulsion. So applying this rule, you can say that 2 is more stable, is stable. Okay, this is rule number, what is that? 6. So you can all try with some examples because I have to do, okay, let me just finish off this. Let me do one question of this. So I'll try to finish aromaticity also here, this today. So question, arrange in the order of stability, or you can say which is the least stable. You can let me ask least stable. Okay, so take down this question. 1. Please apply all the rules, only then you can go. Yeah, can you tell me which is more stable, least stable here? Yes, wishes. N is cannot, nitrogen having the pentavalent. Yes, Lakshmi is right. Bhavanidhi is right. Nurul is right. Yes, yes, yes. Very good. Akhila, Ashwin, all are right. Good. So the rule number, the previous rule will tell you that, you have two positive charge adjacent to each other. Okay, if you see here, many people will have given me once this answer. Here it is separated, nitrogen, oxygen. Okay, so it's different. So you can, just saying this, you can say that two positive charge exists here, so there will be repulsion. So first one is more unstable. Okay, so now we'll go to the last rule. With this, your aromaticity will be, resonating structures will be over. Let me give with a question. There is a very important rule. See, there is CH here, CH here, CH3 here. Then you have another structure. Okay, so this is structure 1, this is structure 2. Now you have the same number of charges, same number of bonds. Okay, there's no other thing. Okay, when you have confusion, so you applied rule number 1. Okay, doesn't apply. Rule number 2, 3, 4, 5, 6, all this doesn't apply. Okay, then you go to the last rule, which is if all rule fails, then apply inductive effect. Okay, now where is the positive charge? The positive charge is here. Here, in this it is here. Now to that positive charge, we know the alkyl group, this group is an electron donating group or electron releasing group. Okay, so you will have the inductive effect towards this because it has a negative charge, it can donate electrons. So now considering that fact, your 1 will be more stable. 1 is more stable because it donate electrons to the CH plus. Okay, but here if you see there's a double bond here. Okay, so you don't have here, it is a CH group. Okay, so we cannot consider that as electron donating group. So that positive charge, the second one, is unstable. Okay, it's just hanging, it doesn't have anything to support by donating electrons. So just apply. So all these rules fail, then go to the last one, that is your inductive effect. Okay, so I hope it is clear for you all. Okay, so now the last part, the next part we will go. So these are the rules for resonance. Okay, now we will go to the aromatic character. So let's see what is aromaticity. So under aromatic character, okay, we'll divide the compounds basically into 3. Okay, that is whether the compound is aromatic. Okay, so we can also call the compounds to be non-aromatic. Okay, then we have something called anti-aromatic. Okay, always remember, with respect to stability, the aromatic is more stable than non-aromatic. Then the last one is your anti-aromatic. Okay, if a compound, imagine you are doing, I'll just tell you. Imagine you are doing a reaction in the lab, okay, and by when you do the calculation, you have an anti-aromatic compound formed. Okay, so it will be very, very unstable. It will undergo rearrangement by itself. Okay, to go to either the non-aromatic part or the aromatic part. Okay, so that unstable, this anti-aromatic compounds are. Okay, so you should know that it is the least stable. Okay, so it will undergo rearrangement by itself. Okay, fine. Now, let me go on to the conditions for aromaticity. What are the conditions for aromaticity? Okay. First conditions or rules, I would say, conditions or rules. Okay. First one, the compound has to be cyclic. Okay. Then we cannot take a double bond, single bond, and a long chain compound and tell that it is aromatic. Okay, the first condition is the compound has to have a cyclic structure. The second one, it should be conjugated. I told you what is conjugation. Conjugated. What is conjugated? Delocalization of electrons. Delocalized electrons. Okay, that is where all did we find the conjugation earlier in resonance? Whether when it can have a sigma pi, it can be pi sigma lone pair, it can be pi sigma positive charge. Okay, so these are the conditions. Now, third one. Another important one is it should be planar. Very, very important. The compound has to be planar. Okay, imagine one group is like this ring, the other one is like this. Okay, so it cannot be. See, one is in this side, the other one is this. So even if you're considering 2-3 rings together, okay, they all should lie in the same plane. Okay, one cannot be like this and one cannot be like this. So the compound has to be planar. So when I am writing the aromatic thing, I will write cyclic as C, conjugated C, again P as planar. Okay, so now planar means it should be in terms of two-dimensional space, I mean. Okay, so now, and you can see in benzene ring everything is sp2 hybrid. And the last one is a very important thing which is called the Huckel's rule. Okay, so this one I am telling conditions for aromatic or aromaticity, for the compounds to be aromatic. So it should obey the Huckel's rule, that is, it should have 4n plus 2 pi electrons. Okay, let us take n equal to, so it can be 0, 1, 2, 3. Okay, so now let us consider n equal to 0. Okay, if n equal to 0, the value will be, this will become 0, 2 pi electrons. So if we have a compound like this with a double bond, okay, you have to tell whether it is aromatic or non-aromatic. One more thing is, it doesn't have a charge, so it can have either a positive charge. So it also has a 2 pi electron. Okay, so a double bond means it is 2 pi, or if there's a lone pair of electrons, that is another 2 electrons. Okay, so I'll give you that examples later, you can just note down. Imagine if n equal to 1, then if you calculate, it will be 6 pi electrons. So your benzene is a very good example. Okay, see here, 2 electrons, pi bond, pi bond. So each pi bond will have 2 electrons. So 2 plus 2 plus 2, 6 pi electrons. So this is aromatic. Okay, and so on. N equal to 3, then you have 10 electrons, sorry, 10 pi, and so on. Okay, so now these are the 4 conditions for a compound to be aromatic. Okay, if it is not aromatic, okay, we have to look in for anti-aromatic properties. Okay, so what is anti-aromatic? The best example would be cyclobutadiene. Okay, so here from this structure you can say that it is cyclic, good condition. Then it is conjugated. Look here, it has a sigma pi. Okay, so it is obviously conjugated. It is, see, only please remember, planarity they will mention to you, because you cannot see and tell. Sometimes, they will draw some structure where you can find out. Otherwise, the planarity point alone will be mentioned in the question. Okay, that it is planar. So third one is, it has to be planar. The fourth one for anti-aromatic compound is Huckel's rule. For aromatics is 4n plus 2 pi electrons, and here it is 4n pi electrons. Okay, so let us take here. Here we will not take 0 because everything will be 0. So if it is 1, we will get as 4 pi electrons. If it is 2, I will get it as 8 pi electrons. And 3, I will get it as 12 pi electrons, and so on. Okay, fine. As I told you, the important thing between aromatic and anti-aromatic is, anti-aromatic is very, very unstable. Okay, even if in the reaction, if some anti-aromatic compounds are formed, it will be very unstable and it will undergo any of the rearrangements possible. Okay, so now what is non-aromatic now? Okay, anything which is not aromatic or anti-aromatic, all those will come under the non-aromatic character. Okay, so let me write the rule or the definition, sorry. Compounds, if they don't show the property of both aromatic and anti-aromatic, all those compounds are said to be non-aromatic. Okay, so you can say anything. See here, if I take this example, I am telling you it is planar. Okay, but see here, it doesn't show conjugate. It is cyclic and planar. but it doesn't show conjugation. Why? Because this is pi sigma sigma. Okay, so if it doesn't show, if there is a charge in this, okay, then that would be aromatic. Okay, so it will undergo conjugation. So this, so it does not come. So this is actually 2 pi electrons. Okay, so now this one, as I told you, it does not show conjugation. So it is not aromatic or anti-aromatic. So this compound will be non-aromatic. Okay, so you can tell anything long chain compounds. Let us take this kind of example. Double bond. This is not cyclic. Okay, so now, so if it's not cyclic, it is not aromatic nor it is anti-aromatic. Obviously, this has to be non-aromatic. Okay, I hope it is clear, and I have told you the rule that aromatic is more stable than non-aromatic, and the last one is your anti-aromatic. Okay, now let us do some examples. So more examples you do, more easier it would be. Okay. So let us take first one. So these examples are there in your book, I think. Let me just. See, this is called, you have to try your IUPAC name also, okay? How many carbons are there? 5 carbons. 1, 2, 3, 4, 5. And there are 2 enes, okay? So it is called cyclopenta, 2 enes, so dinyl carbanion, or you can say anion. Cyclopentadienyl anion, okay? Now, tell me whether it is aromatic, non-aromatic, whatever. Okay, so now first, what is the rule? You have to see whether it is cyclic. Yes, it is cyclic. Conjugated, sigma, pi, you have a lone, you have negative charge, so that is okay. Then sigma, then pi, okay? So it is conjugated, okay? I have told you it is also planar. Because I've told this, they have to tell you with the question. So this compound is planar. Now let us see the fourth one, the rule, that is your Huckel's rule. Okay, Huckel's rule, please remember, you have taken total number of electrons. So see here, there's 2 electrons, and the negative charge is also considered as 2 electron. Okay, so 2 plus 2 plus 2, so it has 6 pi electrons. So this compound is aromatic. Okay. So if they give you a charge, so that's very, very important. So let me take the example of phenol. OH. Okay. So it is cyclic. Obviously sigma pi conjugated. I'm telling you that this is planar. Okay. Now how many electrons? 2 plus 2. How many pi electrons? 6 pi electrons. So this is aromatic. Okay. So now, the third one, let me take the same thing like the first one, okay, but I'm adding, earlier it was a negative charge, but I'm giving a positive charge. So easily you can say it is cyclic, okay, it is conjugated because pi, sigma and a positive charge, so this comes under conjugation. It is planar, but you see here it has a positive charge, so that will not be included, okay, in the electrons. So how many electrons? 1, 2, 3, 4. So 4 pi electron. So if it is 4 pi electrons, we can say that it is anti-aromatic. So you can tell about the stability, it is highly unstable. Okay, I've already told you about the cyclobutadiene. Now let me tell you another one. Okay, yeah, can you tell me what kind of a compound is this fourth one? Aromatic, anti-aromatic, non-aromatic? Third one is anti-aromatic. I want the fourth one. Adarva, check for the fourth one. Dhruv is right. Aditya is wrong. Check whether there is conjugation. Yeah, there was right now. No, Srinidhi, check. Shweta, check. Srinidhi is right now. See here, first what did I tell you the rule? Whether it is conjugated. Okay, first let me take it as cyclic. It is cyclic. Okay, now see here, pi, sigma. No, here this side also it is sigma. So there is no conjugation, The second one itself doesn't apply. For compound to be anti-aromatic, it has to be conjugated. Okay, so no conjugation. Okay, then you can. So the next doesn't apply, though it is planar. After that, there's no question. First was to be cyclic. Second one is to check for conjugation. So when you know that there is no conjugation, please rule out aromatic and anti-aromatic. So this has to be non-aromatic. Here also everything you have to go by rules. Okay, so rule 1, rule 2, follow that and then get. Okay, so now let me give you one more question. Let me check. Can you try this? Tell me what kind of a compound is this? Go rule by rule. For conjugation, check whether it is following any of the conjugation. Pavanidhi is right. Very good. Tanuv is right. Mukhil is right. Dhruv, check. Very good. Srinidhi, Vishisht, everybody is good. I'm seeing only few answering all the time. All of you just try, all of you. Very good. All of you got it. What is the first rule? Okay, cyclic. Obviously, it is cyclic. Now, check for conjugation. There should be alternate bonds or lone pairs. Okay, so this is pi, this is sigma, followed by a positive charge, then sigma, followed by a positive charge, then sigma. See, there is alternate thing, no, and a charge is also there. So it is conjugated. Now, I am telling you that this is planar. Okay, I told you that by default you have to consider that it's planar. Now, how many electrons? 2 pi electrons. Where does it come in Huckel's rule? In aromatic compound. So it obeys. It has 2 pi electrons. So this is aromatic. Very good. Many of you got it right. Okay. Now, so let me give you some questions. Okay, I think this is very clear for you. I don't want to spend more time. Anyway, let me go to the next rule. Okay. See, till now we saw compounds with just like, carbon. Okay, carbon having a alternate single and double bond or, charges and all that. Now we will consider aromatic compounds with a heteroatom. What are the heteroatoms? Okay, in the ring, okay, instead of carbon, okay, you have oxygen or nitrogen or sulfur. So these elements instead of carbon in the ring, okay, so these atoms are called the heteroatoms, okay, or they're also called the heterocyclic compounds, okay. So let's do some example. First, this is called furan. So there is an oxygen instead of a carbon. Okay, and there is a lone pair of electrons. Okay, So now let us see whether it is aromatic or in fact oxygen will have 2 lone pairs. Okay. So now let us see whether it is cyclic. Yes, it is cyclic. Now conjugated sigma pi sigma pi sigma lone pair. Yes, it is conjugated. Now next one. What is that? It is planar. Next one, check for the Huckel's rule. Okay, Huckel's rule. We have to see how many electrons are involved in the conjugation. See, if I write the resonance structure for this electron can move. Then this double bond can move. Then this one will. So only one lone pair is involved in resonance. Okay, you have to take only that lone pair into account. Okay, so now. So totally 2 pi electrons. So it is 4 plus 1 lone pair is entering. So 6 pi electrons. Okay. So we have this one, and 6 pi. So this compound is aromatic. I hope it is clear if you have any doubt. Now let us see another compound with nitrogen. Okay. This is called furan. Furan. Now the same compound, instead of oxygen I am taking nitrogen. Okay, this is called pyrrole. See, some names, get used to it by practice. Okay, so here you see sigma pi sigma and a lone pair. Okay, so you have cyclic, conjugated, and how many electrons are involved? Okay, sorry, here there's only one lone pair. Okay, so now this one will be involved in bonding. Okay, so it will be 6 pi electrons. Obviously it is planar, so this is also aromatic. Same thing with thiophene. You can just check all that with sulfur. Okay, so this is cyclic, conjugated, planar, and 6 pi, because 2 electrons will enter the ring for resonance. Okay, now let us see one more. It's called pyridine. I think you would have heard about this. It is added in alcohol. It gives a very bad smell. Okay, it's called pyridine. Nitrogen in the benzene ring with a lone pair. Okay, so now you see here, well, let me write it. Okay, now it is cyclic. Pi sigma pi. Okay, then you have this lone pair in this one. Okay, it need not for resonance. Otherwise also you can write resonance with the 3 pi bond there, right? So it is, obviously it is conjugated, planar, but here even without the lone pair entering, it shows conjugation. And if it is not involved in the resonance, then please do not count that. So otherwise it has 6 pi electrons. So this is aromatic. Okay, so now coming to the next one, I'll give you more examples so that you get. So suppose if they give you some compounds, set of compounds, and say which is more stable, see which is aromatic, and accordingly you can tell the stability. Let me do another one. This is, so 1, 2, 3, 4, 5, 7, cycloheptane. There are 3 triple bond. So cycloheptatrienyl followed by a positive charge. So this is called cycloheptatrienyl 3 triple bond cation. Okay. So now let us see cyclic. Conjugated, see here. Pi sigma followed by a positive charge. Yes, it is conjugated. Planar. Okay. So now check for the double bond. How many pi electrons are there? 2, 6. So 6 pi electrons. So it is aromatic. The same thing, it is given in your textbook also, I think. This The same thing, cycloheptatrienyl anion if I give. Okay. So now, see, are we counting that electron for resonance is what is more important. Okay. So now here pi, sigma, then there's sigma here. So that means this electron, this negative charge is entering the ring, right? Conjugation. So pi, sigma. Okay. So it is cyclic. You are taking it conjugated because you are adding that negative charge, okay, into the ring for resonance. So now, then it is planar. Now, because you're including that for the resonance, so we have to take how many electrons? 1, 2, 3, 8 electrons. So if it is 8 pi electrons, it is anti-aromatic. Okay, hope it is clear for you. Clear? Okay. Now let us see with some multiple rings. Okay. So all these examples are given in your textbook. So we have something called naphthalene, which two benzene rings are fused. This is naphthalene. It's a bicyclic compound. Then you have something called anthracene, where 3 rings are fused. So you'll be wondering, how do they see all these structures? Because I seen students, ma'am, how do you know these structures? Okay, which is the data I told you when I started benzene. So there is an instrument to find these structures, okay, and they will have to do lot of instruments to do each one. You can calculate and they will arrive at the structure. Okay, so this is called anthracene. Let us see whether it's aromatic, non-aromatic. Okay, it is cyclic and both the rings are in the, so first let us see whether it is planar or conjugated or not. Sigma pi, sigma pi, sigma pi. Okay, then you can also consider, we have to consider, please remember this, you have to consider each ring separately, very important. Okay, now if I consider this ring, okay, then I have to take this double bond also into consideration. Okay, because it is that double bond belongs to both the ring. So it will be pi sigma pi sigma pi. Okay, so please don't think that here many people make a mistake. Here it is pi, so they'll consider this as sigma, this sigma. No, okay, that pi will belong to both. Okay, so each ring you have to consider. Okay, in anthracene, like you will have totally you have to consider, that is pi sigma. Okay, then you will have pi, then sigma, then pi sigma. Okay, so here you have to consider sigma pi sigma pi. Here you have to consider pi sigma pi sigma pi, like this. Okay, so this is also, so now how many electrons here? Cyclic, conjugated, planar, and it is aromatic because there are 10 pi electrons. Now here how many? All are same, conjugated, cyclic, planar. Here there are 14 pi electrons, so this is aromatic. Okay, now just I want to tell you about the consideration of each ring. Another compound is where they get confused. They might attach some groups in the ring, so you don't have to bother about that. You please apply the rule. See, there may be some group here and all that. So all that you don't have to consider. You have to just consider the 2 rings to check whether it is aromatic. Okay. Here, as I told you, it is very stable compound. Okay, and let us see how many. So what they will do for this compound is, okay, they will say, okay, obviously it is cyclic and planar. Okay, so how many pi electrons? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 pi electrons, and they will tell that it is anti-aromatic. but this is not. Anti-aromatic means it's it's unstable, doesn't exist at all. But this is highly stable. So what, as I told you, we have to consider, please remember, for biphenyls compounds, okay, consider each ring for aromaticity. Okay, very important. Now, so if you consider both, it will be 6 pi and 6 pi, then it will be aromatic. Okay. So now let us do one question and end the session. It's a competitive question. Which is the least stable one? Yeah, so I've just asked you, which is the least stable one? Yeah, can anyone tell me? Quick. Yes, Mukhil is right. Dhruv is right. Mubin is right. What? Wow, very good. Everybody has got the answer. Good. Okay. So we can say that this is, I have just told you about pyridine. So this was aromatic. You can check. Okay. We have done this. So this is benzene. Obviously, it is aromatic. Okay. So this also we have done. Okay. This is also aromatic. Okay. Here, okay. First of all, what is this? I just want to explain here. Let me just explain to you. Let me write it. Let me make this compound straight. Let me make it sit straight. Then we can discuss. Plus. Okay. First rule, cyclic. Let us see whether it is conjugated. Sigma, pi, sigma, sigma. See, sigma, sigma, both are sigma. So there itself we will know that it is non-conjugated. So what did I tell you? Once you know it is non-conjugated, because what is the condition for anti-aromatic? Anti-aromatic is it has to be conjugated. Okay, but on here it is non-conjugated. So in case they ask you whether which one is like, can you choose between aromatic, which is the odd one out, why? So you have to tell this is, what is this? This is not aromatic. This is not anti-aromatic. This is non-aromatic, because your second rule for this thing itself fails here. Okay, obviously it is planar. Okay, so we cannot say that it is anti-aromatic. We can say that it is non. So when the second one itself, we will know whether it is aromatic or non-aromatic or anti-aromatic. Okay, so I hope it is clear for you all. Okay, so we can, so next class I'll do about let me just, okay, so yeah, we will do about the stability of the cation, carbocation, carbanion, like how rearrangements will take place. So when I am doing the rearrangement, I'll also tell you about the stability of these things. So anyway, before that, I'll just quickly tell you, like, I was just going on telling you this anti-aromatic compounds are very, very unstable and they will undergo rearrangement. Okay, so let me tell you one important reaction where it will try to form, okay, convert from anti-aromatic, okay, to a more stable form. So this will happen only with anti-aromatic compounds. Okay, so they will undergo dimerization. So I gave you a very simple example. Cyclobutadiene. I told you this is very, very unstable, and I gave you this as an example for anti-aromatic compound. Okay, so it can undergo dimerization. So if I take, imagine, like you will be wondering why I am reacting with one more. See, when I take in a beaker some cyclobutadiene, it is not that one compound. There is Avogadro number of compounds, right? So one will react with the other one. So how it will react, let me just show you. These are the two. So what will happen here? It will undergo homolytic fission here. I told you it will itself go to the most stable state. Okay, it will undergo homolytic fission. So here there are 2 electrons and here there are 2 electrons. Okay, now which was belonging to this part, okay, here, now what has happened? These two are joining and these two are joining. Okay, so now you will get a structure like this. So the 2 double bond has become single bond. Okay, so this is the compound. See how, now can you tell me, this is anti-aromatic. Obviously, this is anti-aromatic. Now it is not gone to the aromatic form, but at least a little more stable form, which is non-aromatic. So you can say it is cyclic. Okay, then it has, so I told you, you have to consider each ring. So this is actually non-aromatic. Okay, as I told you, second point itself, you will know whether it is conjugated or not. So there is no conjugation here. So this is not. So obviously, anti-aromatic has gone to a little more stable form, which is non-aromatic. Okay, so like this, these anti-aromatic compounds will undergo rearrangement, okay, to go to a little stable state. Okay, so I hope it is clear for you. So next class, we will do the other part, the last part, about the stability, about the carbocation, carbanion, and so on. Okay, so if you have any doubts, you can write to the mentor. I'll see to it that, whether I can explain in the next class. Okay, so thank you all. You hope you enjoyed the class. Okay, good night.